Okay, this is still section 3.1. We've been discussing scatter plots and correlation, describing the relationship between two quantitative variables. Okay, a lot of times we use the word correlation when we are describing the relationship between two quantitative variables. And we typically try to preserve the word association for describing the relationship between two categorical variables, although it's not wrong to use the term association. That just means relationship. Okay. When you are comparing, though, two quantitative variables, you are generally given a value called the correlation coefficient, and that is denoted by the symbol R. Okay, that value is describing the correlation, and it is a number between -1 and +1. Okay, now this is extremely important. Just because the correlation may be exactly 1 or exactly -1 does not mean that the points in the scatter plot are perfectly linear. That is a common misconception. Okay. So the R value does not tell you whether the points are perfectly in a straight line or not. It really is distinguishing what the strength of the relationship is. Okay. Technically, the correlation tells us two things. Okay. It tells you the strength of the relationship, and it does tell you the direction of the points in the scatter plot. By direction, I mean positive or negative. Okay, so if your R value is positive, then obviously we would categorize the correlation as having a positive relationship, as opposed to if the R value is negative, then we would say that it has a negative correlation. Okay, but the correlation tells you the strength and the direction, not the form. Okay, not the form. So do not assume that the stronger the correlation, the more linear your scatter plot would be. Okay, and I'll give you an example of this here. You know, of course, we know that a parabola would have this shape here. If you were to, say, zoom in on just these points here, and that only is what your scatter plot was, you might accidentally think that these points here look like they're really, really linear. Okay, they kind of appear like they're in a straight line, when in fact there is a curve to them, but you can't really see it by the naked eye. But if you ran a regression on the calculator would be able to detect that that's actually zooming in on a piece of a parabola, and that a parabola or a quadratic regression would be a much better fit than a linear regression. Okay, something like this, you would have an R value that would show that it's really, really strong, but it doesn't mean that the best fit for that data is in fact a straight line. Okay, here's what you want to think of in terms of the R values. You want to picture basically a number line. Okay, and picture all the way on the left is where R is -1, and all the way on the right is where R is +1. In the middle would be where R is 0. Okay, anything that is on the outskirts here, any R values closer to -1 or closer to +1 are considered very strong correlations. And as the R value gets closer to the middle, where it equals 0, then we are talking about an extremely weak correlation between the two variables. Okay. Now, you are not expected to calculate the R value by hand. Almost always you would get that value from your calculator and from having ran a regression. Okay, but I think this formula may be on the formula sheet, and the part that you just want to make sure that you're familiar with is the fact that how the R value is calculated is it's calculated from getting the z-scores of the x coordinates of your point and then multiplying that by the z-scores of the y coordinate of your point. Okay. Now, the reason that I mentioned that is when we talk about transformations, we know that measures of center and location are affected by multiplication and division and addition and subtraction. measures of spread are only affected by multiplication and division, but we learned that the z-scores are not impacted at all by any transformation. And so what that means is the R value, or the correlation, it doesn't change when the units of your data set change. Okay, so if you were to change from feet to inches and then rerun that regression, your R value is not going to change. Okay, and that is in part because the R value formula is using z-scores, and z-scores are not affected at all by transformations. Okay. All right, so you can see a little chart here. Okay, here's a chart that has some different words that you can use to describe the strength. Okay, you'll notice the closer you get to -1 and +1, that's where we're talking about having a perfect negative or perfect positive correlation. Okay, this should never tell you whether it's linear or nonlinear. So notice here we are only using a strength word, and then we're also using a word for the direction, which would be negative, of course, if the R value is negative, and positive if the R values are positive. Okay. Typically, we say that it's strong when it's between 0.75 and 1. Moderately strong, maybe between 0.75 and 0.5, and then we start getting weak, and then obviously 0 is non-existent. And so what we're going to do here is we're going to take a look at these scatter plots here. Very small underneath these, they list what your correlation would be, your R value. And you get a sense here that, you know, this was negative, looks like that's negative 0.99, and how this is so much tighter clustered together. Okay, that strength increases the less spread out your data values are. Okay, but here you can still see that they're kind of clumped in more of a negative trend, but it is much more weak for that. Okay, so the question is, how strong is the correlation, and is it positive or negative? That's what we want to just kind of use this rough chart here to kind of categorize these. Okay, if the number's positive, we're clearly going to say then that it's positive, but 0.235, we're going to call that positive and weak. Okay, here this would be negative and weak. 0.975, we might say that that's positive and maybe very strong, because we're getting really close to 1 at that point. And this one would be negative, and maybe we would call this like moderately strong. Okay, there's no hard and fast rules to the adjectives you choose, but just know, just kind of think back to this right here. The closer you're getting to -1 or 1, you want to increase your vocabulary with saying that it's stronger. Okay. Okay, the question here is which association is more linear? Okay, one that has an R value of 0.5 or one that has an R value of 0.9. And this is kind of a trick question here, because we know that we're not supposed to be able to distinguish the form by exclusively looking at the R value alone. And so we would want to say, wait, you can't determine the form by using only the correlation. You would want the scatter plot to actually look at to determine the form. R is just a supplement for the graph. It is in no way a replacement. So you really need to be able to see the graph in order to make a comment about the linearity. The R value will only tell you about the strength and the direction. Okay, strength and direction only. Okay, so we had practiced in the previous video going through the acronym DUFS for describing a scatter plot. Okay, and we said this is direction, unusual values, form, strength, and we always want to make sure we're using context here. Okay, so you can see what we have in this is we have the boats that are registered in Florida. This is by the 1,000s here. And then this is the number of manatees that end up being killed as a result of these boats. Okay, and they did give us that the correlation was 0.79. Okay, so we can say the data suggests that there is a, okay, we could call this strong, probably fine if you chose moderately strong as well. The data suggests a strong, positive Okay, and I can get those words from either looking at this R value, or I can get it by just kind of observing the scatter plot. Okay, but then I definitely need to be glancing at the scatter plot to say that it's linear. Okay, because it does look like there's not really much of a curve there. Relationship between, okay, here's my context, between boats registered and manatees killed. Okay, and then I'm just going to kind of use real world terms here. What does that mean when it's got a positive relationship? As the number of boats increases, the number of manatee killed increases. Okay, that's what a positive correlation means. As one variable goes up, the other one also goes up. Okay, let's look at another one of these here, only this one has an R value of 0.4. Okay, here we have our explanatory variable as the storms that are predicted, and then our response variable is the storms that are observed. Okay, this doesn't really feel, I mean, it has a slight positive correlation to it here, I guess. Okay, but it does feel somewhat spread. Okay, we definitely get that here, that this is positive, but this is definitely weaker. So we're going to say the data suggest a weak positive. I am going to go ahead and call this linear relationship between storms predicted and storms observed. As the storms predicted increases, the storms observed increases. Okay? All right. So that is that explanation there. Okay? Now, I want to make sure that we are refreshed with how to use our calculator to run a linear regression. In AP Statistics, we will only be running linear regressions, okay? That is the only one that we will run, okay? And first and foremost, I will tell you, if you go to my website, there are some calculator video links that will walk you through how it looks and what the key punches are in the calculator. If you want to see it done on the calculator, you can go watch that like less than 5-minute video on how to do that. It is very important before you run a regression, though, that if you want it to report the R value for you, you have to make sure your diagnostics are turned on. And this would be explained in the video, but you need to go to the catalog, second 0. You need to scroll down to the command diagnostic on. You need to press enter twice. That will then show you the R value when you run a regression. Okay, you're going to enter the X values into L1 and the Y values into L2, and you get to that by pressing stat and the edit key. Okay, you will then proceed to press the stat button, bump over to the calculate menu. This is a little bit different. We typically choose option 8 instead of option 4 because in AP Statistics, we use this B value for our slope and the A value here for our y-intercept. Okay, and when you run that, then the R value should appear at the bottom of your screen. Okay, so we're going to go ahead and try that here. It would be good for you to walk through this on your calculator. The X values are always what you're going to input into L1, and the Y values are what you will input into L2. I will tell you, if you have any old data already stored into your calculator when you go into your list, and by the way, again, this is where you're going. You're going to press stat and edit. If you already have numbers here, then you need to go and move the cursor on top of L1. You're going to press the clear button followed by the down arrow, okay, and that will clear all the data in that column for you. Okay, you're going to fill it up with these body weights, then you're going to bump over to L2 and you're going to put the Y values, the backpack weight, into L2. Okay, after you've done that, you'll proceed with these steps here that we talked through. Okay, once again, before doing any of this, you need to go into the catalog and turn the diagnostics on. This is simply asking you to find the correlation, and then we're going to go ahead and use that to describe what it tells us about the scatter plot. Okay, if you run that, you can pause the video if you want to go ahead and run it and try it there on your own. The R value should be 0.79. Remember, this does not tell you anything about the form. We don't know if it's linear or nonlinear unless we actually look at the scatter plot. But what the R value does tell us is that the correlation is positive, and we could call this strong. It would be okay if you wanted to call it moderately strong. Okay. Okay, here is a second example. If you wanted to try another one, here would be the R value that you should get if you try this one. We would categorize that as very strong and positive. Okay, here's just some facts about correlation that are worth noting. Okay, I will tell you that the correlation, the R value, it is heavily affected by outliers. So if you have an outlier in your data set, it will weaken, potentially could weaken, or I guess it could strengthen. It just depends on where it's at. And I'll give you an example here. Let's say that you have a scatter plot like this, okay? And then you have this extra point, but it's way up here, okay? In this example, this blue extra point, which does kind of look like maybe it's an outlier because it's lying out away from the rest of this data, that blue outlier is actually strengthening the correlation because it's falling in the pattern of where your line of best fit would land. Now, if I were to erase that and move it, say, down here, well, in this case, now the outlier in that location is actually weakening your correlation, and it's bringing that R value closer to 0. Okay. Other things worth noting is that your R value will not change when the units of measurement change. Okay. And the correlation doesn't actually have a unit. So when we say that the correlation's 0.98, we don't label that with any unit of like what our X or our Y variable are measured in. Okay. Okay, the last page here on these notes looks at that idea of the R value, it doesn't really distinguish between what your X and Y variables are. So for instance, if my explanatory variable is miles and my response variable is price, and I run a linear regression and I get an R value, and then I go back through and I now put the price as my X variable and the miles as my Y variable, I'm going to get the exact same correlation. Okay, and this is in part because the R is calculated using the z-scores of both the X and Y variables, okay? And the z-scores are not affected by changing the units, okay? So that makes no, and I've seen AP questions before ask, what happens to R if everything in the data set were either multiplied by a number or if the explanatory and response variable were swapped? Nothing happens to R. It stays exactly the same, okay? And as I mentioned on the previous page here, you can see that in this first example on the left, here we have an outlier, okay? And you can see how the line of best fit would be dragged a little bit closer to that outlier if it's placed there. If the outlier were actually removed from the data set, well, that makes the correlation so much stronger. It makes it bump up to 0.7 from 0.4. Okay. It does depend, though, on where the outlier is. If the outlier is not in the same pattern of the points, it weakens it. But if it is in the same pattern, it could actually strengthen it. Okay. All right. So it says here is a scatter plot of the sprint time and long jump distance from data that we looked at earlier. The correlation is negative 0.84. Interpret the value of R in the context. Okay, now please keep in mind the R value only tells you two things. It will only tell you the strength and it will only tell you the direction. So here we can say the data suggests. Now, this is if you're only looking at the R value and you're not looking at the scatter plot. If you have the scatter plot to look at, you can absolutely comment on whether it appears linear or nonlinear. But if we did not have this to look at and only the R value, which is what this is asking us to interpret the value of R, we would say the data suggests that there is a strong and negative association or correlation between sprint time and long jump time. Okay. What effect does this circled point right here have on the correlation? Well, it might be making the correlation just a little bit weaker, okay? Just slightly weaker, because it does kind of feel like the points are higher when the x values are lower. And so as we move over here to the right, we would expect maybe these values to be getting lower. And this point here is maybe a little bit higher than what we would expect happening with this trend. So not dramatically, but I might just say that that outlier, it makes the correlation a little weaker because it's higher than expected. Okay, because it's higher than expected. Okay, we're not going to do anything with this right here. We don't need to worry about that. That is a good place for us to stop. There should be some problems listed